I'm going to pause and erase this. Okay, so now I'm going to show you what psi negative squared is going to be. So this would be n squared psi a squared plus psi b squared minus psi, 2 psi a psi b. So because now you have a minus sign, this is the overlap density, this whole thing. And so because you have that minus sign, what you then end up getting, and I shouldn't have erased it, so this is A and this is B. So here you had, this was the sigma bond, but then what you're going to get is something that looks like this. So it's going to go up like this. And then at this point, you're going to have something that looks like this. So the two waves are coming together and one is positive and one is negative. And so when they come together, now the probabilities cancel in this region. So destructive interference. And so you don't have any electron density in the center, but you do have electron density out in the outer regions. So we call this a sigma star or anti-bonding orbital. Cool. And so the anti-bonding orbital involves destructive interference, and it's also the imaginary wave function. So the real wave function is going to be the positive, where you have constructive interference. The imaginary wave function is going to be the destructive interference, and so combined you have both the real and imaginary, giving you a complete representation of your system. Okay, pause me if you want to write all that down. I'm going to jump to the solutions of the Schrodinger equation. Hello again. Hopefully this is a little bit more efficient so you're not watching that long of a video and you can just pause me when you need. Okay, so you've got the real wave function, which is the constructive interference, and you've got the imaginary wave function, which is the destructive interference. We're now going to put these linear combinations into Schrodinger and we're going to determine what the energy is. So the energy we're going to have based off the constructive interference, the energy is going to be the energy, the energy of the H1s atomic orbital. So this is the hydrogenic H1s atomic orbital energy. So that whole function that you get with the n squared, h bar squared, and all that goes here, plus J0 over R, which involves the repulsion between the two nuclei, minus J plus K divided by 1 plus S. Okay. Go team. And I am going to just quickly, okay. So we've got some terms here. Now let's go through them. S is our overlap integral, and that is equal to integral psi a psi b d tau. So again, that's the overlap density that you would have. The J is equal to the Coulomb interaction, or Coulomb integral, and that is equal to J0 times the integral psi a squared divided by RB d tau. And this is the interaction between the nucleus and the electron density on the other nucleus. Okay, so this is the interaction between the nucleus A and electron density around the other nucleus. So you can't just necessarily separate it out that there's only electron density here. Because of the linear combination, you've now created electron density also on this side of the other nucleus. And so you've got this energy, or this wave function, this nuclei now interacting. and having an energy of interaction with the electron density on the other side of that nucleus. All right, and that's represented by this J here. And then and then K, you'll see all this. K is equal to, this is what's called the exchange integral. And that equals J0 integral psi A psi B per RB d tau. This is the interaction between the nucleus and excess density in between due to the overlap. So not just on the other side of the atom because of this part, but now it's due to this part. Okay, so this is the interaction between nucleus A and excess, or sorry, overlap electron density. Again, all this is in Atkins, but I wanted to take you through it because it's a lot. Okay, cool, sweet. So the other thing I want to note is that the only difference between, so this is for the plus, we also have a minus. So we also have the anti-bonding or the destructive interference or the imaginary component. So we want to look then at how this changes. And the only difference here is for the negative, this becomes a negative and this becomes a negative. Cool? Awesome. Okay. That's all I got for now. Oh, one more thing. I'll stand back, pause me. I'm going to draw a plot of the differences in the energies plotted as a function. So how does this change with R is what you'll see in the next segment. Hi. Okay, so I've got E plus and E minus written with the energy of H1s plus J0 over R. And I should have mentioned, sorry, J0 is shorthand for E squared over 4 pi epsilon naught. And that's why we call, so J, the integral, is known as the Coulomb integral, and J0 is just the integration, or the Coulomb potential when you don't have additional overlap energy density with just two charges. So E squared over 4 pi epsilon naught is J0. Okay, so the plot that I want to show you is 9B.6 or 10.17. This is specifically, so let's look at the purple one first. This is the energy as a function of R normalized to A0. So the purple is for the positive. This is looking at the difference between, so just looking at this portion. We've moved, so the positive energy minus, or the constructive interference energy minus this energy for H1s, and these two values should be the same, energy of H1s, energy of H1s. So we're looking at the difference between there, just so we're plotting this part. So for the sigma bond, that's where that comes from. There's your Morse potential. Go team. But when you plot the negative for the sigma star, you get something that looks like, actually starts farther out, like that, sigma star. So this is your negative energy. And notice that at large R, the energies are the same. And so that's where you get your ionization energy, when the electron density and the wave function describing it has changed such that you now have this energy of the free particle. Okay, so what's really cool about this is think about what each of these energies represent. So here's your equilibrium energy, okay? And if I just said each one of these is an energy that you have said, okay, H psi equals E psi. And at this particular radius, say there, you have a wave function, and that wave function is going to represent the difference between all of the different electron densities, and then you take the square of that, that's the probability density, integrate probability distribution, and that gives you one energy. Then you change ever so slightly R, and now you get a slightly different energy. Well, that's because you have different wave functions. those wave functions change because when the Hamiltonian operates on it, it's going to change the wave function that represents it. There's going to be an equilibrium, but these represent the average, or I guess basically the expectation value of where you're most probably going to find if you take a series of measurements. Cool. I think that sums up MO theory for us. And the last thing I'm going to do a podcast on Garada and Ungarada. So go team. Email if you have questions. Yay.